This reference guide is the first reference guide for Unit 7, which will deal with designing systems of equations. All of Unit 7 will involve working with systems of equations. For this reference guide, we're not going to get too far into the math involved in systems of equations. All we're going to be doing is figuring out how to design them, how to set them up so that they can be solved, which is what we'll be looking at in subsequent reference guides. So for today, we'll look at setting these things up. In reference guides 2 through 5, we'll look at solving them. So when we talk about a system of equations, which is also called, as it says here, a linear system, we're talking about two or more equations that are related in some way. These equations will each have two variables in this course, and we will be figuring out how we can solve these pairs of two variable equations so that we can get values for each of the variables. Again, we won't worry too much about that last part, about getting the values, but we will in future reference guides. So what we'll be doing is we'll be setting up systems of equations, or we'll be looking at a problem and we'll be generating two equations from that problem. Now, in order to do this, we'll need to assign variables, and we'll need to define those variables as we've seen done in the past, and we'll need to ensure that everything that we are setting up is accurate, because we can't solve the equations if we don't set them up properly, or it's very unlikely that we would be able to. All right, so there's no new terms, or there's nothing that's really brand new here. We looked at the end of Unit 6 at setting up equations, whether it be in slope-intercept form or even in point-slope form. We're just extending on that. So now instead of just setting up one equation, we're going to be setting up two. And there's three problems that are on this reference guide. The first two are done for you. We're going to go through those as we always do, and then we'll do the third one together. But as we go through the examples, I want you to pay attention to where both of the equations are coming from. Because again, setting up the system of equations is just as, if not more important than solving them. Because if we can't set them up properly, we're not going to be able to solve and get appropriate answers for the values for the variables. So example number 1 reads, a school district has buses that carry 12 passengers and buses that carry 24 passengers. The total passenger capacity is 780, and there are 20 more small buses than large buses. So we can see in everything that I'm underlining in blue that part of this information deals with the number of passengers. So one bus holds 12 passengers. One type of bus, the other type of bus holds twice that. It holds 24 passengers. And in total, if we take all the buses and we figure out how many they all can hold, the answer is 780. So we can hold 780 students in total. And now if we look at the information that I'm underlining in red, we have some information that deals with the number of buses. Not the number of passengers, but the number of buses involved. And I've underlined that in red. So we know that in terms of our total number of buses, which can hold a total of 780 passengers, 20 more of the buses are small, or they hold 12 passengers, than are large. They hold 24 passengers. Okay? So when we do this, when we're setting up our systems of equations, the first thing that we need to do is just get a sense of what information we're given. And there will always be two types of information in these questions because we need to create two different equations. And in this case, the first type of information that we know deals with passengers. We know that there are buses that can carry 12 passengers and buses that can carry 24. We also know that in total there is 780 passengers that can be carried in total. The second thing that we know doesn't deal with passengers. It deals with number of buses. And that information tells us there's 20 more small buses than large buses. So we make sense of the problems that we know the avenue that our equations are going to take. Now, the first thing we do when it comes time to actually start writing on our paper is we assign variables or letters to each type of bus. So each question may not deal with buses. Whatever it is, you have to define your variables. And when we talk about defining variables, this is what we're doing. We are saying let, in this case, S represent the number of small buses, and we are saying let L represent the number of large buses. Now I want to be clear on something that I've been clear on in the past, which is don't just state let S represent small buses. You have to be specific. So what about the small buses? Well, it's the quantity. It's the number of small buses. So S represents the number of small buses. L represents the number of large buses. And again, we don't use equals. We don't say let S equal number of small buses. We use that word represent. Because in this question, it's representing it. In another question, S could be used to represent something else. So we don't say equals, we say represent. So the first thing we do is define our variables. Once that's done, and we look back at the question and make sense of the information found therein, then we can come up with the equations that we're going to be ultimately solving, just not in this reference guide. So with the first one, we're talking about number of passengers. Well, every small bus there is holds 12 passengers. So that means that 12 multiplied by S will give us the number of passengers that are on small buses, so 12S. Likewise, every large bus holds 24 passengers. So 24 multiplied by the number of large buses is the number of passengers that are found on large buses. And we know that the total number of passengers on small buses plus the total number of passengers on large buses has to equal 780. So 12S, number of passengers on small buses, plus 24L, number of passengers on large buses, is going to equal the total number of passengers, which is 780. So that's our first one. Our second equation deals with number of buses. We know that there's 20 more small buses than there are large buses. So the number of small buses, which we've denoted with an S, is equal to the number of large buses, which we've denoted with an L, plus 20. So 20 more than our number of large buses gives us our number of small buses. And that's as far as we're going for right now. Those two equations that you see on the reference guide, that was set up your linear system. It's now set up and it's ready to solve. We just don't know how we're going to solve those just yet, but we will when we get into some future reference guides like 2 and 3. Okay, question number 2 we'll move through a little bit more quickly because it's also done for you, but we'll talk about some important points to this question. So again, we're setting up our linear system. That's what question A is asking us to do. So the linear system that we need to set up is the perimeter of a Nunavut flag is 16 feet. Its length is 2 feet longer than its width. So we need to figure out how we come up with perimeter. Well, we know that perimeter is the distance around the outside of something. So if you think back, we can remember that perimeter is 2L plus 2W, or L plus W plus W. So P equals 2L plus 2W. 2 times the length plus 2 times the width. That will give us the distance around the outside of this rectangle. We know that the perimeter of the flag is 16 feet. So the first equation that we're going to deal with talks about perimeter. So we know that 2L plus 2W will give us our perimeter, and our perimeter is 16. So therefore, 2L plus 2W must equal 16. And if you look a little bit down to step 3, so I got a little ahead of myself with that, but you can see that equation is there. The other equation still deals with the flag, but now we're talking about its dimensions. We're not talking about its perimeter, we're talking about its dimensions. And we know that the length is 2 feet longer than the width. And this is kind of like the bus question before, where we had our number of small buses is equal to our number of large buses plus 20. Well, now we know that our length is going to be equal to our width plus 2. And we'll get to that equation here in a minute. But we know that one equation will deal with perimeter, one equation will deal with dimensions specifically, length and width. Okay, so again, when we start this question, we define our variables. And we went through this last time, so we'll go through it a little more quickly this time. But in this case, We're talking about perimeter, which is 2L plus 2W, and we're talking about dimensions, which is L and W. So we're talking about length and width here. Those are the variables that we're going to use. Those will be the two variables that will appear in each equation. So we'll let L represent the length of the flag. We'll let W represent the width of the flag. Again, we're using that word represent, and we're specific in what it is in fact representing. And now we get to our two equations, and we've already talked about the one that's in red. Well, the question tells us that the perimeter is going to be equal to 16. We also know that in order to find perimeter, we use the equation 2L plus 2W. So we can see in step number 3, when we generate our first equation right here, that 2L plus 2W, which is the perimeter, equals 16. And the question tells us that the perimeter is 16, so we just put our equation for perimeter in and set it all as equal to 16. The second equation, again, it corresponds, or it's similar to, rather, the bus question before. The length is 2 feet bigger than the width. So whatever our length is going to be our width plus 2. So L equals W plus 2. Okay? And again, we have set up our linear system here. First equation deals with perimeter. Second equation deals with dimensions. We're not solving it just yet. Now, question B, or part B, does ask us to solve something, but we're not going to be using any of the strategies for solving linear systems to get here. So let's be more specific. Let's read part B, and then we'll talk about the answer that's there. Denise has determined that the Nunavut flag is 5 feet long and 3 feet wide. We're using our linear system that's created to verify that she is right. And all we're going to do with that is we are going to plug in the value 3 for width and the value 5 for length. So where we see L in our formula that's circled in red above, we're going to plug in a 5. Where we see W in that same formula circled in red, we're going to plug in a 3. And that's what you can see happening over here to the left. This is our formula that we circled in red above, and we've just plugged in the 5 and the 3, the 5 for L, the 3 for W, which gives us 10 plus 6, which equals 16. And now a major caution for this unit, and this will extend beyond just reference guide 1, is if you verify something, verify it with both equations. Because sometimes, and it is rare, but sometimes it will work with one equation. The numbers you get will work with one equation, but not necessarily the other one. So to cover all of your bases, when you are doing checks, take the extra 30 seconds, if that, check in both equations. So our other equation was L equals W plus 2. Well, that's the one that's circled in blue above, and we're told that our length is 5 and our width is 3. So we're saying that 5 should equal 3 plus 2. We all learned a long time ago that it does. So both equations check out, which means that the answers Denise got are valid. And again, in future reference guides, we'll talk about how we're going to come up with those answers, because we will ultimately be generating answers to these, and we'll figure out how maybe she got 3 and 5. Okay? Not today. That's for future reference guides. Example 3 has not been completed on the reference guide, so we're going to do that one together. So let's do that now. So creating a linear system to model this situation. In Calgary, a school raised $195 by collecting a total of 3,000 items for recycling. The school receives 5 cents for a pop can and 20 cents for a plastic bottle. So we'll see that there's two things happening here. There's something that involves money. So they raise $195. 5 cents comes from pop cans, 20 cents comes from bottles, and they collect 3,000 items. So our first equation will deal in cost, our second equation will deal in numbers, but before we do anything, we need to define our variables. So we'll do that. So we will let C represent the number of pop cans. And of course, it doesn't matter if you chose a different variable instead of C, that's fine. And we'll let B represent the number of bottles. So the first step has been completed. We have defined our variables. Now we're going to come up with our equations. And the first one we talked about as cost. 5 cents 20 cents, $195. So we have to convert our 5 cents and our 20 cents into decimals, or into dollars, which we do by making them decimals. We divide each by 100 because there's 100 cents in a dollar. So if each pop can gives us 5 cents, well, 5 divided by 100 is 0.05. So to figure out the money that comes from the pop cans, it's going to be 5 cents for every can. 5 cents times however many cans there are. If it's 20 cents for every bottle, well, 20 divided by 100 is 0.20 multiplied by the number of bottles. And if we add up our money from cans and our money from bottles, we're going to get $195. So our first equation, which deals in cost, is done. 0.05, or 5 cents for every can. 5 cents multiplied by number of cans, plus 20 cents for every bottle, 0.20 times B, is equal to $195. So we have everything there in the correct denomination. 0.05, 5 cents, or $0.05. 0.20, 20 cents, or $0.20 equals 195. Now the second equation is just our total number of cans plus our total number of bottles equals a nice even 3,000. So they collected some number of cans. When you add that to the number of bottles they created, you get 3,000 total items. So there's our two equations. That's a linear system that would be ready for solving now if we were a couple reference guides further. But we have set up our linear system. We've defined our variables. We've set up our equations. Part B, we have answers now. We're told, or we have what we're told are answers. We're told that the school collected 2,700 pop cans and 3,000 plastic bottles. So we're going to make sure that our linear systems are right, and we're going to check those answers. So let's do the one in red first, because that's the easiest one to check. We have 2,700 cans. So where I see a C, I'm going to plug in 2,700. Where I see a B, I'm going to plug in 300. And 27 plus 300 equals 3,000. And we know that there were 3,000 items collected. Tells us that in the question. So our red equation checks out perfectly, and that's pretty straightforward. Our blue equation, we'll have to do a little bit more math, but calculators may help us here, or will help us here. So let's plug that in. Remember to check both equations. Just because it works with one doesn't necessarily mean that it will work with the other. Oftentimes it will, but don't take the lazy route and don't check both. Make sure you're checking both. So 0.05 times 2,700 is 135. 0.2 multiplied by 300 is 60. And we know that 135 plus 60 equals 195. And 195 equals 195. So that checks out. What we want is the same number on the left of the equal sign and on the right of the equal sign. If that happens, then you can be confident that both of your checks have worked out, and you can be confident that the linear system you set up is correct. And in this case, it is. Okay? And that's as far, as I've said before, that's as far as we're going with this reference guide. In reference guides 2, 3, and beyond, we'll start looking at ways to solve these linear systems that we've created.